Today we're going to talk about radioactive decay and how it helps nuclei reestablish stability when they become unstable. The root of the word is one that you've seen multiple times. If we analyze the components of the word radioactive, we come up with two parts, radio and active. Radio is referencing the electromagnetic spectrum. It basically tells us that energy is being emitted as these particles decay. And decay obviously means fall apart. Active means that these atoms are active on the electromagnetic spectrum. They are giving off energy. We're next going to talk about how this and why this happens to various atoms. Some of the essential questions we're going to cover in this video are: why are some atoms radioactive while others are not? We've already briefly talked about the fact that it has something to do with this concept of stability. And then how do nuclei stabilize when they are unstable? In order to discuss this, we're going to start by taking a look at a graph. Before we get to the graph, though, it's probably useful to review some key components of atomic structure. The key components of the atom are protons, neutrons, and electrons. Protons are positively charged, and they are located in the nucleus along with neutrally charged neutrons. Electrons are negatively charged, and they are located in the shells outside of the atom. The key thing to look at here is that positive and neutral particles make up our nucleus. Normally we think about opposites attracting, but remember our electrons are out in their shells and they're not located in the nucleus, so they can't attract with the protons. What we end up with is a big conglomeration of positively and neutrally charged particles. There's no real electrostatic reason for them to stick together, so their size of the nucleus becomes pretty important. Let's start by taking a look at the graph that I mentioned earlier. When we look at graphs, it's best to take in some information that is written on the graph before we start looking at the visual representation of the data. On our y-axis we have number of neutrons, and our x-axis is number of protons. So, as you can see, there's a line that's red in the middle where the protons are equal to the neutrons, and the data points line up with that line initially before deviating from it later on. If we look at our key, we see that our stable nuclei are in blue in the middle, making up some polka dots. And then we have some colors showing what the nuclei look like when they're not stable. Our green line, it looks like there's more neutrons than there are protons, and those would be considered unstable nuclei. Those neutrons have a hard time sticking with the protons in the nucleus because there's too many. The yellow line below the kind of area of stability shows nuclei that have too many protons. They have an opposite problem with the ones we just discussed, but the result is the same. They are unstable nuclei that need to find a way to get back to the zone of stability. The orange area above show nuclei that they don't particularly have an issue with the ratio of protons to neutrons necessarily, but they are rather large nuclei that are unstable just by having too many and neutrons jammed together in the nuclei without any negative charges to hold them together. If a nucleus has too many neutrons, it can undergo beta decay to become stable again. When this occurs, a neutron is changed into a proton and an electron is emitted. The proton stays in the nucleus and the electron leaves the nucleus. In this example, we see a carbon-14 atom. As you can see, the mass number is on top and the number of protons in carbon-6 is on the bottom, converts into a nitrogen-14 atom that has 7 protons, and an electron is leaving the nucleus. In order for this to happen, since the atomic mass doesn't change, we don't lose or gain any protons from the nucleus. Merely one neutron that has a mass of 1 and a charge of 0 undergoes decay and changes into a proton, which also has a mass of 1, but a positive charge. And in order for that neutron to no longer be neutral, something had to happen to a negative charge if a positive charge is left behind. So we know that an electron, which doesn't have a mass and has a negative charge, has to leave the nucleus. We call this beta minus decay. I remember that because the electron is negatively charged. Minus signs and negative signs are fairly interchangeable. And you can see that this type of decay would allow an atom that has too many neutrons to drop one step closer to that zone of stability by getting rid of a neutron. Notice the mass doesn't change. It remains 14 the whole time because neutrons and protons have the same mass on an atomic level. Beta plus decay is what occurs when the opposite problem is occurring in the nucleus. There's too many protons. This process is quite similar to beta minus decay in that one of our nuclei particles, in this case our proton, changes to the other, in this case our neutron, so you'll notice the mass still doesn't change, and a positron is emitted. A positron has the exact same mass as an electron, which is 0, but instead of having a negative charge, it actually has a positive charge. Now, the positron is emitted when that proton loses its positive charge to become a neutron. Remember, neutrons have the same mass as a proton, so we still have that 1 added to our atomic mass, and instead of having an extra proton, we'll notice that our atomic number changes. It goes down by 1, and the element is converted to the one that immediately precedes it on the periodic table. In this case, magnesium 12 turns into sodium, which has 11. In order to complete the reaction that I've drawn below, we have our proton, same mass as the neutron, with a positive 1 charge, converting into a neutron, no charge, same mass, and a positron. Remember that positron is emitted from the nucleus. You'll notice that our mass and our charge are conserved after undergoing this reaction. We still have our 1 unit of mass from our proton and our +1 charge. They've just been rearranged, much like we talked about when we were balancing equations. Mass and charge are balanced in this particular equation. In our final form of radioactive decay, alpha decay, the nucleus is just too large. The ratio isn't exactly the problem, it's just that there's too many protons and neutrons there, making it unstable. In this form of decay, we essentially emit a helium atom, and here's how. You'll notice our mass changes by 4. We lose 4 atomic mass units from our nucleus, and the atomic number changes by 2. So the protons must have changed by 2. Well, if you look at the periodic table and you look at helium, it has a mass of 4 and 2 protons, and therefore 2 neutrons. So we really say that helium is emitted from our nucleus. As you can see, both mass and charge, through atomic number in this case, are conserved in this equation as uranium-238 decays into thorium-234. Now that we've discussed all 3 forms of radioactive decay that we're covering in this class, let's head back to our graph. Once again, we can see our stable nuclei in the center, and now we know the mechanisms by which elements are able to decay back into that valley of stability, otherwise known as the zone of stability or the line of stability. Once again, notice that line is not quite 1-to-1. It starts off that way, but then deviates as it moves across into higher numbers of protons and neutrons. And if we think about what we just learned, we know that beta minus decay happens when there are too many neutrons, and that neutron decays into a proton and an electron, which is emitted. That would move an nucleus from above the zone of stability back down into that zone of stability. It might have to happen multiple times, but eventually the nucleus would get there. Similarly, if we look below the valley of stability into the beta plus emitters, we would see that an element with too many protons could decay into that zone of stability by losing a proton, having it turn into a neutron, and have a positron emitted. Finally, our alpha emitters are just too large. 2 neutrons and 2 protons are given off to get it back down into that zone. Now notice, it might start in the orange, move to the yellow, and then go into the zone of stability. That just means that it would undergo alpha decay first before moving back into beta plus emission to cause it to get into that zone of stability. These decays can happen in a chain, one right after another, until that nucleus is once again stable and found in the zone of stability. If you have any questions on radioactive decay, please let your teacher know, and you can go ahead and get started on the practice problems to test your understanding of these concepts.